First of all, we are going to present a new project, a new subject, about full flow modeling for lost form casting process. But let's present who we are. So we are a group of computing and fluids at Cemef. Cemef is one of research center of École des Mines. And in this group, we have too many activities that goes from fundamental, applied mathematics, computational physics, okay? And we'll show you some example on that. And we have a tight collaboration with Transvalor, especially on the fluid part that we use in Tercast or Rheology. So to present all the activity that this group is doing, in one slide, it's so complex, but I did it. So this is the poster presentation, how we read it. First of all, the three words, applied mathematics, fluid mechanics, parallel computing, fundamentally speaking, and applied mathematics speaking. And this can give us access to a process like polymer processing or phase change in quenching or heat treatment in industrial furnaces, and even casting and filling. So you see that there is, for material forming, there is a representative of fluid in each of these applications. That's why we are a group on that. And also, we open access to new application, new processes, such as aeronautic, aerodynamics, and etc. Always we visit them in a perspective or parallel computing to be most state-of-the-art on this subject, and also to challenge our solver in new application in extreme events when we go to aerodynamics and other application. So this is open the perspective for many applications, such as one of them, the lost form application. I will let Rudy present it.
Maybe most of you know this process. So the principle is first to obtain a foam pattern. Okay, so most of the time it's made of polystyrene. So the design can be done with your preferred software like Rem 3D or something. And then, so you make this pattern. So it's based off a polystyrene foam. So you have to age it in terms of maybe evacuating the gas, residual gas, and also get the final dimensions. Then you can assemble the patterns and build the cluster. So it's very familiar for the casting process. Then you put it in your in a bath. So to make a coating, and this coating will have some various properties. So it will be a barrier to the liquid metal when you cast it, but it will be permeable to gases and air, and it's very important, you will see, because of the local physics. Then you compact the cluster in the sand, as usual in normal casting processes, and then you pour the metal, and this is where we will focus later, and you extract the cluster, right? So the known advantages for this kind of process is that it's simple, inexpensive, it's easy to produce complex patterns because of the first pattern process, and it requires, as we have been told, a minimum finish. Meanwhile, the physics is quite complex, especially when you do the last part of the casting process. So I will let Elie talk about the...
This is how we work. So even if we have a new process, we need to understand it, first of all. And then we zoom on the physics and the process and the flows that take into account. And then we decompose every part on that, and we see what is missing. So we are not going to revisit Navier-Stokes because we have already a Navier-Stokes solver, but we need to extend it to porous media for the sand part. And there is other parts for error estimator when you have three phases, not only one phase or two phases. You have three phases to deal with that. So you need an error estimator that accounts for multi-criteria adaptation. And so on. For conjugate heat transfer, when you have two materials that you need to interact from one to another one. And also, of course, interface capturing to be the most precise possible, either with level set or phase field approach. And so on. Physics at the interface where we come back and we see what is happening for this physics. Usually, if you know, for any two-fluid flow, we have surface tension and we have other physics like that. And finally, the phase change, which is very important because you create the bubbles and the bubbles goes out. So with this focus is very important for numerical part, and then we need to check what we have at the numerical part ready for that. Almost on the numerical solver we are ready. So in this project there is the physical part that will be deal with Rudy. So to let you know about the numerical part, we will put in place, or we will use the error estimator for, especially here, multi-criteria adaptation. There is a conservative interpolation. If you have something going on and you remesh the whole time, every time you remesh, you interpolate your solution, and you need to be conservative on that. And this is a very important point, especially for precise interface motion. Second point, to be the most robust or most performance on parallel computing, and this is thesis, we have some thesis on that. And finally, the immerse method, when you have to deal with multi-domain, two solid or two solid and fluid, so fluid sector interaction. So we have this immerse method that deals with any kind of immersed object like you see here. You have phase change for a ring, you have several material inside a furnace, and you have the anisotropic mesh adaptations that deal at the same time with the solid, the two bracket, and the flow. And the flow is very important here to speak about the boundary layers you see that are captured very well, and the vorticity and the flow characteristics. So finally, we are pushing forward moving mesh if needed in this project. So on the numerical part, things are ready. And what we want to do now is to go to the physical part. Okay, and we'll tell you the good news at the end of the presentation. So for the difficult part.
Okay, I'll come back to the first diagram, which describes local physics. When I mean local, it's like at every point of the domain, there is something happening in terms of heat exchange, mechanics, etc. And so you could consider a lot of different things. So Elie has been talking about the solvers. Let's talk about maybe the basic physics. So you vaporize the polystyrene, and the velocity of vaporization will give you mostly the velocity of advancing front. It's just that you create here a kind of mix between liquid metal and gas and polystyrene vapor. So you don't really know if it's an interface, or something like this. And then you have to evacuate that. So there's always a weak point in the physics that drives the speed or the efficiency of your process. So mostly, if you have a nice process, so you vaporize, you evacuate the residuals, and then you move on with your front. It's a slow process, and it's not that interesting. Equally, if it's too fast, maybe you can have. So this is the liquid metal. This is the foam. Maybe the front will change its convexity and will advance like this, and you can have merging fronts in complex parts that can create here a big bubble of polystyrene that won't be evacuated through the walls, because here you have the coating that is permeable to the gas. So you entrap bubbles or something which is like a gaseous phase with metal, and then your part is completely crap, right? So you can have this kind of problem. You can also have this kind of problem, which is an instability of this front, which is quite complex because it's very local, and you have a kind of Pac-Man flow, right? So you eat these bubbles, and then you find them later in the part. So what we have done, using the basic tools we have implemented a very average physics. Sorry, I will come back to this one. We just defined the fact that actually if you have time or not to evacuate this gas through the walls, you will have a velocity of the front will be in advance at the center or late, right? So it's a very simple physics. It doesn't describe the bubbles, but it's the zero order model. And then what you can do is, with the tools Elie has been talking about, you can describe, so this is the liquid metal, this is the foam. You can describe an advancing front, and it can take into account complex topologies. You will see it can be arbitrarily complex. And then you can see that the process is going well, okay? With the same physics, so you define a certain characteristic length of the physics. You can also describe merging fronts. So here it's in advance, the metal is in advance, right? And you will see that you will entrap a bubble of polystyrene. So this, at the end, will be some polystyrene. It's gonna melt and then give a gas bubble. It will go up depending on the sign of the gravity. And obviously, this kind of simple model can be implemented in 3D situation, as you can see here. So it's a very simple automotive part, but it's just for illustration. So we can deal with complex topologies with the numerical method we have so far been using.
So finally, the full flow modeling, it would need advanced numerical method to do that. It's almost ready. We are putting it into a place to prepare a proof of concept, which is very important. And this proof of concept interests now PSA. And this is the good news. We have a big project starting with PSA on this subject. So this is how we work, by combining numerical approaches and computational physics on a subject, decomposing it into version 0, version 1, version 2, and so on. And the loss form modeling, we are understanding what is happening. Now we take the version 0 just to check, and then we can increment the physics in this direction. Okay? With the help of a partner like PSA, we can have like experimental result or industrial test case to make some confrontation. So all that will go into integration into Tercast. This is also another good news. Okay? So the project will start officially in March 2020. And everybody here is welcome to join as a partner on this project. Thank you if you have any questions.